we touched on derivatives in the last unit. We talked a lot about limits, and limits are the fundamental sort of building blocks of derivatives, but the derivative is an important thing, finding the slope of a tangent, right? So we're going to do more derivatives, and today we're looking specifically at polynomial functions. So here's something you didn't see in MHF. It's just a little bit harder algebra. It is a cubic function, and it's a lot hard. It's harder because, so get this written down, everybody, quickly, please. I've got it copied out here, so you can just write it right down. It's kind of long because you got to really expand. If you look here, the cubic expands to something pretty big. But if you remember back from grade 11, I'm sure you learned about Pascal's triangle and binomial theorem, so you can expand it really quickly. And then, are you getting this down okay? And then when we come down here, you can see that the terms, wait. Do you want me to show you an easier way to do this? This is kind of long. It's like a whole page. Let's take a look at an easier way to do this. Let's start all over again. I'll show you a little trick that'll help us streamline this process a little bit. How's that sound? So we do want to revisit a little bit first what a general polynomial is, what it means. And you probably saw something like this in MHF. If you didn't, that's okay. All of the A's are coefficients of each term. So again, when we talk in generalities in mathematics, we don't give it a specific degree. So the degree is n, where n could be any not integer, any whole number, right? Any positive integer. Not rationals, not negatives. Those aren't polynomials. We talked about that previously. So a to the n is the leading coefficient, and then x to the n, and then n minus 1, n exponent n minus 1, dot, 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 however many you have, and then the coefficient of the second last term. Thank you. Here's your... and then the constant at the end. So A0, or sometimes we call that, like we use C for constant. Okay, so an example of that would be just like 3x squared plus 7x minus 1, right? So polynomial, that's all we're talking about, but could be any number of terms. Okay, so here we go. Here's some rules for derivatives. This won't maybe make a whole ton of sense until we start actually using it, and we are going to look at a few proofs eventually, but bear with me to get started. So a constant function, what is a constant function? A constant function looks like this. If y equals c, some constant, so there's no x, it's x to the 0 there, then y prime is 0, or we're gonna go back and forth using the different notations. No reason why we choose one over the other. Not today, at least. Just to get us used to using the different notations and remind us how they all work, because we will flip back and forth throughout the course. There are times where we tend to use y prime, or we tend to use dy by dx, like in mathematics, but you know, they're sort of subtle and they'll come up throughout the course. But for now, we're just going to kind of use them interchangeably. Okay. So this is kind of by definition. We've seen this before a little bit, but we're sort of defining some things right now. So what this means is, if I have a line, and the line would be y equals c. So c might be 5 here, or 100, or whatever. Obviously, it could be negative as well. And then this value here that it's going through is c, right? It's a horizontal line. That's what it means to be a constant. We saw this, I don't know, a week ago or so, and people were a little bit like taken aback. And you got to be reminded that if a function equals a constant, it's just, that means it's a horizontal line. Everybody okay with that? Just a quick reminder, that was something. Here is something new. This is big. Folks, this is big. First step into a whole new world. If my function equals x to the n, and remember today we're just talking about polynomials, then f prime of x equals n x to the n minus 1. So, in other words, we bring the exponent down out front and reduce the exponent by 1. So, for example, f at x equals x to the 4. Okay, so if you're busy writing, I want you to watch. This is really important. And I'll stop and let you get a copy down. Then f prime x is 4x cubed. Okay? F prime x is the derivative. It's the slope of the tangent. It's an expression. This is the same thing we were doing in the previous unit and in MHF. We did it with the difference quotient. Either the x approaches a version or h approaches 0 version. Okay? We used both those versions. The x approaches a was from MHF, and we learned a new one. To find derivatives, to find slopes of tangents. And then remember, we did the expression of the slope of the tangent, or the expression of the derivative, the general derivative. This is the same thing. So I found the general derivative without using the difference quotient formulas. Okay? Everybody got that copy down? We're okay? Constant multiple rule. These, if these seem, I don't know, like constant multiple rule. I mean, that's like a made-up name. Like, it's not, we don't really care about the name of it, but it's important to know, and it will be easy. Like, you'll start using this. Actually, what's interesting is you will very quickly be using all of these rules without thinking and without remembering what the actual rule is. This is a good example where you're going to use it over and over and over again, but then be required to use it in a different way down the road and not be able to apply it. And that's normal. Like, that's not a criticism, but just, it's interesting kind of thing, right? So it's one of those things where it might seem like technical, but we use it 1,000 times in a really simple way. But there is something deeper. So if f at x equals k times g at x, then f prime x equals k times g prime x. And when you look at that, you might not be able to really understand what that's getting at. I mean, it's pretty straightforward, but you might not like, okay, well, what that looks like, it might be complicated. Now we're using a lot of function notation, and we are going to get into a lot of function notation, okay? But when I look at a very simple example, and this is the kind that you will be using over and over and over and over and over again. So if y is negative 7x cubed, y prime is negative 7 times the derivative of x cubed. What's the derivative of x cubed from the thing we just did above? John? Very nice. 3x squared. So y prime is actually negative 21x squared. You certainly would not do that in 2 steps. In other words, you do the derivative of the variable part, and when you take the exponent out front, you multiply it by the coefficient. Right? See what I'm saying here? So we typically would not show that middle step. And see how simple that is? Okay. Any questions so far? We need to do a couple more little tricks to really have some power here. I want you to go ahead and do that first part. In fact, if you like, you can move on to B and C as well. See what I mean by some function notation here? This is something we want to get used to. What we're about to do next is something that you would probably find intuitive. You'd probably guess. You'd probably do automatically, assuming it's true, which is the wrong thing to do. Okay? What's a good example of something we assume to be true? You don't anymore. You all, if you're here, I hope you know this is not true, but back in grade 9, grade 10, we assume it to be true, and it is absolutely not. Does anybody know of a good example of that? There's another one we did in MHF. That exponents are distributive. That's something that intuitively people think is true, and it's not. Here's another one. Right? That I don't know what that even means. You factor a 2 out? Like, I don't know what that even means, right? But this is not, I hope you remember that that's not true. So neither of those are true. Those are examples of things that we assume to be true because they kind of look like something we're familiar with, but it turns out they're not. Okay? And we're going to find, in fact, very soon that the first thing we're going to look at here, we would assume to be true, and it is, but the other thing we would assume to be true, and it's not. We're not going to see it today, but. Okay, so go ahead and find G prime and H prime. I'm worried if you're writing, you're not listening, but that's my fault. Oh, you already did it. Very good. How are we doing with this? Andrew, can you give me G prime? Very nice. How many people got 8x? We got 8x, right? It's pretty straightforward. Very good. Who wants to give me H prime? 6x squared. See how easy this is? See, everybody thinks calculus is easy. At first, at least. Okay, very good. So function notation, f at x, if f at x is g at x plus h at x, so then f at x would equal, there's no work here to do. Mary Lou, did you do it? Hold on, if this is the, I think you gave me C. You can give me B too, right? Yeah, very nice. We're just literally taking those two monomials and adding them and calling that f. Okay, and then what is g prime x plus h prime x? Okay, this is, I'll do this one. 8x plus 6x squared. So what do you notice about that? So what we would assume, I think, is that if f at x equals g at x plus h at x, hello, then f prime equals g prime at x plus h prime at x. This is what we would assume, that I can take the derivative of each term individually. So what we would assume is that this expression here is f prime. Do you understand what I'm saying? But that's an assumption. We don't know that to be true. How would we prove that? Can anybody take a random guess at how you might prove a rule like this, or for that matter, the other rules above? John? How would we do that? What do you mean by that? Okay, good. So if we tried to use the ones from today, they don't cover this yet necessarily. Like, that's what we're building. What could we use that we've used in the past?
We know that the derivative of function is 1 degree.
Ah, we do. So that fits. Yeah, Jason, what were you going to say? Yeah, we could use the difference quotients, the x approaches a or the h approaches 0 formulas. Now, they're a bit tricky. They're in the textbook. I'm not going to cover them. We may look at them in class at some point. I'm not going to cover them now, but you need to look them over. They're in like the textbook section, not the practice question section, right around the homework from today. So take a look at them. Take a look at them over this weekend. Proofs are something that you will be required to cover. That's all I'm going to say about it right now. But you need to look at them. They're quite straightforward. These ones are easy. So that's why we're not going to take the time to look them over together as a class. But it's hard because the notation's hard and you're just not used to proofs. But these are not complicated proofs. Okay? So there's other proofs that are coming later on that are much more complicated. But the proofs for the things we're doing today are pretty straightforward. Yeah? So write down, sorry, what? Yes, because it is true. We assume it's true. And this is what I was saying, is we assume this one to be true, and it actually is. With a star, that G and H are differentiable. So you can only take the derivative of something if the individual parts of it are also differentiable. Some things are, some things aren't. There are some things that are not differentiable. And so if G happened to be one of those things, then you obviously can't take its derivative. So you couldn't take the derivative of f either, right? For polynomials, this is all trivial. Because polynomials are made up of monomials, and that's what we've already looked at. Okay? Just because, but see, it looks like a proof. Oh, I wanted to mark this down. This is not a proof. It looks like a proof because if I took the derivative of this and the derivative of that, I'd get this. But the point is, we don't know that this expression is f prime. It is because I'm telling you it is, but we don't know that without a formal proof. And that, as I said, you can find that in the textbook. But it turns out it's true, okay? So for example, if y is 5x squared plus 8x plus 3, dy by dx. So I take the derivative of the first term, 5x squared, so that's going to be 10x. I take the derivative of the second term, 8x, which is just 8, right? Take the 1 down. It's got an exponent of 1. I take the 1 down. 1 times 8 is 8. Subtract the exponent. So it's x to the 0. What's x to the 0? Anything to the 0 is 1. So the exponent, sorry, the variable's gone. And what is the derivative of a constant? 0. So plus 0. Oh. In fact, I'm going to write that down. X to the 0, just so we've got a... But again, we would skip that part. 10x plus 8. Okay? So now so this is the same f at x and g at x and stuff and h at x that we were using before. Well, f at x is different because now f at x is g minus h. Before it was g plus h. So g was 4x squared and h is 2x cubed. And g prime is 8x. And h prime is 6x cubed, so minus 6x squared, I meant to say. And so then we ask the same question, and I think you could pretty easily tell if the sum of the derivatives, if that one was true, the difference has to be true as well, right? Because subtracting is really just adding negatives. Like it can't be true for one and not for the other, really. So if f at x equals g at x minus h at x, then f prime equals g prime minus h prime. Again, as long as g and h are differentiable. Are we okay with this? Any questions so far? Whoops. I should have like a y or something in here. Okay, so why don't you do y prime for this one? Emily, what is it? Everybody get that? Put your pencil down and watch. Do you recognize that? 2x cubed minus 4x squared plus x plus 1. It was that thing that we sort of jokingly started with. So the old method, look what it would have taken, and including, now we didn't do expansion of cubes really. Like in MHF, we didn't really give you questions where it had a cubic. So we haven't practiced expanding a cubic. You do probably need Pascal's triangle and binomial theorem to do it. Otherwise, it's a bit of a disaster. You could do it the long way, but my goodness, it would take. Last year, the MHF classes that I was doing, we did a lot of these, and it's a lot of hard. It's hard. Like there's a lot of challenging algebra there. We didn't do any for whatever reason in MHF this year. But this is what it would take. Look at this. It's a page long. 6x squared minus 8x plus 1. Now we can do it literally in one line. That's better, I think. Don't you think? That's a lot easier. So, and then last year I remember I had a student who had already taken calculus and was upgrading his marks. And he's like, sir, do I have to do it? But yes, sorry, you have to do it that way because we even though there's an easier way, it's important to know where it comes from. It's important to know the original formula and explore those things right before we start using shortcuts. So, and this particular student said to me, like, I never really knew how to do it the other way, but he learned, and then he did really well in the course, and he learned how to do it with the X approaches A or the H method, even though he already knew how to do this one. So just because you know how to do this one, if you're ever asked to use the difference quotient, you got to go back and use the difference quotient. Or the definition of a derivative, you got to go back and use it. You're not allowed to use these rules. Does that make sense? That may come up throughout this course here and there a little bit as well. And the proofs go back to using the difference quotient. Right? All right. Everybody got that written down now? Ready to move on? Let's just do some examples. Now, first example is trivial. You can go ahead and copy it down and do it. After that, pretty much every example is like a very quick brush up of our exponent skills, looking at some different cases. But basically, like, you need to be excellent at working with integer and rational exponents as of today. So that's a big part of what we're going to look at. Which, now that I think about it, we're talking about polynomials, and then we're going to look at a bunch of things that aren't polynomials. But the rules will apply to these other things as well, so there you go. One thing we don't tend to do is if you're given the question in function notation, f at x, you would do f prime at x. If you're given y, you would use y prime or dy by dx. We don't really usually switch between those two. If you were given f at x and then you said y prime, that would be a little weird. Just so you know. Everybody got this one done? Go ahead and do it. Cox, can you give me this one? Got it. I think people are probably in their heads like hesitant because like, it can't be this easy. There's a trick. I'm doing something wrong. No, it's that easy. For these ones, especially for polynomial like that, and you're going to do 100 of these, not for homework, but like over the course of, in this course, we'll see polynomials. We'll see polynomials as parts of bigger functions. In MHF, we do rational functions. Rational functions have a polynomial top and a polynomial bottom, right? So we'll see those. So overall, it's more complicated, but there will still be parts that are just polynomial. So you're going to do that kind of stuff 100 times. But what about this? Is this a polynomial? We talked about this the other day. Not a polynomial. Why is it not a polynomial? Because technically polynomials don't have negative exponents, and this has a negative exponent in it. But it turns out anything you can write like this, those rules that we looked at apply for these as well. And whenever you're looking, if you can turn some expression that otherwise isn't in polynomial form, if you can turn it into polynomial form, especially today, like there are other things that you can do, but this is all we know how to do as of today. So that's what you always do. Take whatever you have and apply prior knowledge, prior skills, prior understanding to put it in polynomial form a plus b plus c plus d, ax plus bx squared plus cx cubed, whatever, and so on. Turn it into that form, and then take the derivative. Okay, so this one is going to be the derivative of 5 is 0, so that's gone, right? 7 times negative 3, negative 21x. Reduce the exponent to a 6. Does anybody want to take a crack at the next part? Because it's a little bit different. Aleph? Very nice. When you reduce a negative, it's actually getting, it's not negative 2, right? Negative 4, we're going down. I'm sure most people probably got that. Maybe that didn't catch you, but sometimes our brain plays tricks on us, and we think reducing means getting closer to 0. But no, it's getting smaller. So negative 3 reduced by 1, negative 3 minus 1 is negative 4. I could rewrite this 6 over x to the 4. How do you rewrite a negative exponent as a positive? It takes the reciprocal. I believe in the homework you're not required to do that. It's really, at this point, there's no rule. It's based on instructions. If your instruction said leave all answers with positive exponents, then you would have to do that on a test. Yes, you might be required to do that. It's certainly something you need to know how to do, right? Is take care of a negative exponent both directions. We took a positive exponent that was in a denominator, turned it into a negative in the numerator. To be able to differentiate, it's certainly something you would have to be able to go the other direction as well. Okay. Okay, let's keep going. What do you notice that's different about this one? If you were in my class last semester, you know, I tried to talk a lot about, like, people think observations need to be profound. And small things that you observe are not important, but I totally disagree. Whatever you observe is important to you. Like, not maybe really important, but it's just something that stood out to you. That matters. That's a big deal. And it's a chance for you to reflect on, are my observations relevant? And even if they're not relevant to what they're doing, they're still relevant, like absolutely. So Max, what do you think? Yeah, it's not in function notation, thank you. There's something else related to that I find interesting. Okay, so what's going on there? Yeah, anything else? It's brackets. We haven't seen an example like this. You know what do you think we should do with the brackets? Right? That's kind of builds on what I was just saying, is this isn't in a form. There are rules to differentiate this as is. In this case, you probably wouldn't. You probably still would expect. But we do have rules. We don't know them yet. We're going to learn them later, but there are rules. But for now, all we know is polynomials, so we're going to expand and turn it into polynomial form. Yep. You could. Yeah, it's not fully factored. No, that's not going to help us. We're not going to do that in this case, but you absolutely could. The other thing that I noticed very simply is it's S's and T's instead of X and Y's. Why is that? This looks to me like some kind of speed over time form, like S for speed. Sometimes S is used for displacement, I think, which is really confusing. But like for distance, so maybe it's distance, maybe it's speed. I don't know. So T greater than 0, it's time, right? So T is, or maybe it should be greater than or equal to. I don't know, but maybe that's what this is talking about. So it's some kind of application. In this case, we would do ds by dt. So we are differentiating s in terms of t. And when you get deep into calculus, it becomes strange because you get more than 2 variables, and you have to pick the variable that you are differentiating in terms of. And I mean, it gets like a lot different from what we're seeing here, like just more complex, more complicated, right? But baby steps, you get there eventually. So it becomes important to talk about what variable you're differentiating in terms of. Anyway, so it's not always dy by dx. It's just y and x because those are the variables we're using, right? S and t, it's ds by dt. And we're not actually ready to do that yet. So let's expand first. 4t cubed minus 12t squared. Now this is something that I can differentiate. 4 times 3 is 12. Reduce the exponent. 2 times 12 is 24, so minus 24t. We all right? Yes? No. In that case, it's always, at this point, there are no rules. It's always dependent on either instructions of the question. Maybe I want you to do that because maybe I want to, like maybe I'm assessing your ability to factor. Or I'm assessing your ability to manipulate negative exponents. So I give you those instructions. But in the real world, it's like, it depends on what you're doing next. If this turns out that it's an equation and I want to set it equal to 0 and solve, which we're going to do a lot of, absolutely you would factor it because that's how you solve a quadratic, right? Like when we set it equal to 0, that's how you solve a quadratic by factoring. So absolutely, under those circumstances, that's what we would do. But in this case, there are no circumstances, so you would just leave it. If you go to the back of the book and the back of the book for some reason has a factored form, then I guess you'd have to factor it to check your answer. I don't know. What does this look like? Anybody? It doesn't look like anything we've done yet today. Kind of looks like a rational expression, right? It's got like a polynomial on top, polynomial on bottom. We're not going to learn how to do those kinds yet. This one's a little bit different. Honestly, it's like a made-up question. It's like a textbook question, and there's a few in the textbook, so we're going to practice one so you know how to do it. But it's just sort of made up again to test your mechanical skills in this stuff. It's different because the bottom is a monomial. So if the bottom is a monomial, I can do this. And I remember talking about this last semester, where this is something that we don't often do, but we see it a little bit when we do trig identities. And it turns out that it's actually kind of a useful little trick. It's the opposite of adding fractions. You get a common denominator and actually add the numerators. So I could split it up into this. And then, what can I do? Anybody see what I can do? Because in this form, this is also not something we know how to differentiate. Yeah, so what would that look like for the first one? Yeah. Yeah, so 5 over 4 x to the negative 1, right? Power rules. Grade 9. Dividing powers with the same base, what do you do? Subtract the exponents. Same thing, and I had to take the 5 over 4 as a fraction out front. So 8 minus 3 x to the 5. All this incredible math that we do. And people will get questions like that wrong because of the fraction. Because we learn how to do fractions, but we kind of learn them in a bubble. Like in grade 9, you do them, but you do them in the fraction unit, and then you barely touch them for the rest of the course. You don't see them much in grade 9. Or you don't see them much in grade 10. You don't see them much in grade 11. You see them in little pockets here and there. And you just muddle your way through it. We never really get comfortable with fractions. And all I could say is, I mean, you're probably going to really have to at this point. In MHF, you kind of did. We saw a little bit more. And in calculus, we will start to see more. So the fact that I have 5 as my coefficient and 4 as my coefficient, and I can pull that out into 5 over 4, I bet that's something that some people wouldn't have done naturally, wouldn't be all that comfortable with. That's something that you need to get comfortable with. Now I can differentiate this. And now look what I have to do. I have to multiply my exponents by the fraction out front. This first one's not too hard, but right, we got to start doing this stuff. So 5 over 4 times negative 1, that's just negative 5 over 4. decrease the exponent by 1, so to the negative 2. Negative 3 over 4 times 5, how would you do that? Yeah. And I know your calculators can do this, and you can get away with it for the most part, but it's a lot better if you challenge yourself and try a little bit to get more comfortable with fractions. Even if you let your calculator do the work to make sure the answer is right, get more comfortable with these ideas so that you can follow along what your calculator is doing is always a good idea. Everybody okay? Any questions? We got a bunch more examples here. Actually, just 4 more. All right. I want you to try this one on your own. We got a long weekend this weekend, man. That's nice. Get Monday off. So we'll be back together on Tuesday. On Tuesday, we're going to do something kind of interesting where, we'll try to make it a bit more engaging than you guys just sitting here taking notes. But I think a lot of this unit is going to be a little bit of like sitting here taking notes. Like we're learning some skills. There's a lot of skill building here. I know it's boring, but it's kind of the way it is. And then in future units, we're going to get into applying this stuff a lot. And then you're going to wish we go back to the boring stuff because some of it's hard. Try that one on your own. You can try F as well. So I'll give you a hint. The first one's ready to go, right? You don't need to do it, and we don't need to manipulate it. You can just employ those rules. There's nothing about it that's weird. Yeah. So I can just, go ahead. Megan, do you want to give me that first one? X squared plus X. Somebody who had not been following what we're doing would be like, this is black magic. How in the world did that work out to that? But if you go over it slowly and use the rules that we now learned today, 3 times a third, well, that's 1. So your coefficient works out to be 1. Reduce the exponent by 1, so the 3 becomes a 2. And then same thing happened here. This question was obviously set up this way. 2 times a half is 1, so my coefficient is 1. And then 2 reduces. That's got a 1 on it, right? Okay. And then what about the pi? Where'd the pi go? Oh, I thought you were going to say I ate it. It's a constant. Very good. Thank you for reminding all of us that pi is a constant. It's a funny constant. It's a special constant in that it goes on and on forever and never repeats, but it is still a constant. So derivative of it is 0. Very good. Next one, also ready to go. How many people are done F? Or maybe almost done? Oh, not quite. Required a little bit more work. Oh yeah, I think this is the first example where we're seeing fractions in the exponent, but it's no different if the fraction is in the exponent. You do it the same way. And what is that way? I take the exponent, multiply it by the coefficient. So what is 6 times a third? 2x. Reduce the exponent by 1. By 1. The number 1. So what is 1/3 minus 1? Negative 2/3. Nice, thank you. Yes. Not like reducing the numerator by 1. It's not 0/3, right? It's negative 2/3. So the next one, what's negative 5 times 2/3? Jason? Good. Negative 10/3 x. And if I reduce 2/3 by 1, go ahead. And then the last one, so, oops. The coefficient is 1. So when I multiply that, I just get that. And negative 5/2 minus 1, how do you do that? Like calculator, I mean, we'll do it, but also you think of common denominator, right? 5/2, or negative 5/2 minus 2/2. So this one should be negative 7/2. Two more examples. What do you notice about G? Emma? The square root signs, Max? Same thing, yeah. You got a couple of square root signs. One has an x, one has an x cubed under it. One has a square root in the denominator. What can we do with the square root sign? Square root sign is just a different notation of a type of exponent, right? So that's what you want to do 100%. So this is equal to 3 times x to the 1/2 minus 6 times, you could do this in 2 steps. We'll do it in 2 steps, I guess, but you would probably want to get to the point where you're doing this in 1 step. Whoops. If I want to do it in 2 steps, I need brackets. So this is x cubed all to the 1/2 plus 4, I'll do both of these, over x to the 1/2, 3x to the 1/2 minus, so what's the power rule? Again, from grade 9, power of a power, exponent of an exponent, you multiply them. So this is negative 6x to the 3/2, and then plus 4x to the negative 1/2. And then we do the same thing. Go ahead and try that one. Check your answer if you like. Okay, last one, I'm going to take one step here. Whoops. And do this. G at x. What's G at x? There is no G at x. So this is just a function notation thing. Anybody want to take a guess what you would do? Like what you would do for this one or write for this one? What's the first part? Yeah. What's the next part? Very nice. I like it. If you remember, way back up, whoop, not that quite that far, right there. If f at x is a constant times g at x, then f prime x is a constant times the derivative of g at x, whatever that is. Who knows what g at x is? G at x could be anything, as long as it's differentiable. So that's just a function notation thing. But again, that can be very useful, very important. Any questions?